All right, everybody. Well, welcome back to another session of CE 397, Control Theory for Smart Infrastructure. So let's quickly just recap what we covered last time. So last time we covered a rather interesting topic, in my opinion. This is one that I think is interesting both for your education, but also for research as well. We looked at controllability and observability of dynamical systems. So can anyone refresh me on what controllability means for an LTI system? What makes a system controllable? Does anyone want to volunteer just an answer for when is a system controllable?
For any initial state, I can, with a finite series of inputs, drive it to the zero vector statement.
Exactly. So that is the exact definition of controllability. A system is controllable if we can find some set of inputs U to drive us from any initial state in the state space to the origin over some time interval T naught to TF. Okay, and we also talked about reachability, which is essentially the opposite. Can we drive a system from the origin to some desired final state anywhere in the state space with some set of inputs U? And for linear systems, those two definitions are equivalent. If a system is controllable, then it is also reachable. And remember, Jimmy also had an interesting point last time. So if a system is stable, it will eventually be driven to the origin even without an input, right? But I noted that stability doesn't necessarily imply controllability. So why is that?
Is it because the steady state of an oscillator is only achieved as t goes to infinity?
Right. So we have to drive the system from any state to the origin over some time interval T naught to TF for it to be controllable over that interval, right? If it's just stable, meaning that it approaches the origin, or if it's asymptotically stable, meaning that it approaches the origin, it won't necessarily reach the origin in that time interval because you can pick any initial state in the state space, right? Right. So being stable doesn't necessarily imply being controllable. And remember, for a linear system, if it is controllable, it is also reachable. So those two are equivalent for a linear system. Okay, so good question. All right, so we talked about controllability. What does it mean for a system to be observable? This one's a little bit more abstract. What does it mean for a linear system to be observable? Anyone other than Jimmy want to answer? Anyone want to just give a guess? Kind of a conceptual definition like this one. What does it mean for a system to be observable? Do you have an idea of what makes a system observable? Okay. So does anyone, including Jimmy, want to answer whether a system is observable? Oh, sorry, what was that? Right. So that is correct. So a system is observable if we can reconstruct the internal state of the system at any previous point in time, given only a time history of outputs and a time history of inputs to that system. And in particular, the ultimate test is whether we can reconstruct the initial state, because if we can reconstruct the initial state, that means we can determine the state at any other point in time. Right, so that is the definition of observability conceptually. We also gave some conditions for determining whether a system is controllable or observable. Okay, so in particular, a system is controllable if and only if the reachability gradient which we defined as follows for a continuous time system, is invertible or full rank. And similarly, a system is observable if and only if the observability Gramian, defined as follows for a continuous time system, is invertible or full rank. And we showed for the discrete time case how using these Gramians, we can essentially either determine the inputs that drive a system to some desired final state, or to determine the initial state given some time history of inputs and outputs. In particular, both of these Gramians are related to the pseudo inverses, right? So the reachability Gramian is related to the right pseudo inverse for an underdetermined problem. And the observability Gramian is related to the left pseudo inverse for an overdetermined problem. Okay, we also gave another condition, an easier to use condition for determining whether a system is controllable and or observable. Does anyone remember what that condition was called? So it's okay to look at your notes, yes. Kalman rank condition, right? So we defined the following matrices, right? So if we have a system and we want to determine whether it's controllable, we can look at the following matrix: B, A squared B, all the way to A n minus 1B. And this is for A in our n by n. And for a matrix, if we're trying to determine if it's observable, sorry, if a system we're trying to determine if it's observable, we create the following matrix: C, CA, CA squared, all the way through CA n minus 1. And what is the condition that's required for controllability for this matrix? What does this matrix need to be? Or what condition needs to hold for this matrix that we've constructed for it to be controllable? Rank. So it needs to have a rank of n, exactly. Similarly, this observability matrix needs to have rank n. All right, so I would say review those concepts. They will be on the final homework, so you'll get a chance to practice these concepts. But controllability and observability is a really interesting topic. So not only can you determine whether a system is completely controllable or completely observable, if you are trying to either control that system or estimate its internal states, you can also use it for related problems such as actuator and sensor placement. So if you're interested in, where are the optimal locations to place sensors in a given dynamical system, like maybe a power grid or a water distribution network, you can use these concepts to try to determine optimal sensor placement techniques for maximizing its observability, or optimal actuator placement techniques for maximizing its controllability. So it's a really, really interesting and rewarding subject to look into, and one that I think is underexamined in civil engineering, because most civil engineers don't learn this stuff. Okay, so with that, let's go ahead and first of all, are there any questions on controllability or observability before we move on? Yes.
So the formal definition is defined over like some time t, right? So that is to say, we're talking about, unless we're taking the infinite time horizon specifically, whether it's controllable in this time interval, but is there a case where it wouldn't, if it's controllable over one time interval, why wouldn't it be controllable over a different time interval? If I can just kind of offset it more, I don't know if
I would need to find a counterexample. I don't know if I can think of one off the top of my head where it would not be controlled. Yeah, given that the input is not constrained in any way. But I can see if I can find a counterexample for you. Yeah, that's a good question. I think for the discrete time case, one could think of examples where if you're trying to observe it over some set of time steps, there are cases where you wouldn't have enough time steps to observe the system completely. For control, well, actually also for control, yeah, if you're working in discrete time, like for instance, let's say you have a network, like a water network or something, and you can input some inputs at the upstream branches, and you want to be able to control the states at every single location in the network. To control the states at the downstream branches, you have to wait until that signal propagates downstream. So yes, it does, you're kind of using the system to control those states where you don't have direct control inputs. So yes, the time interval does matter, yes. Okay. Good question. Okay, any other questions on observability and controllability? Again, this is a really fascinating subject and one I would recommend looking into more on your own time, especially if you're interested in these questions about sensor or actuator placement. All right, so with that, today we are going to look, finally get into control of multivariable LTI systems. So again, revisiting this concept of control that is the namesake of this class. Just to give you a quick preview of where we're going, today we're going to be looking at full state feedback control of multivariable systems. On Tuesday of next week, we'll be looking at observers for the first time. So you'll get your first introduction to state estimation. On Thursday's class, I want to look at two techniques for optimal control and estimation of LTI systems called linear quadratic regulation and Kalman filtering, respectively. And we'll show how those two concepts are duals of one another. And then the final day of class, Tuesday, before your presentations, I want to look at model predictive control, which is a really important control technique. So that's where we're going. Today, we're going to be talking about full state feedback control. And this is something that's going to look somewhat familiar to concepts that we've already explored. It's going to look, in particular, very similar to our discussion of PID control from kind of the middle of the course. And what we're going to show is essentially a generalization of PID control. So whereas with PID control, we could only put in, we could only feed back the state and its derivatives and integrals. In full state feedback control, we're essentially designing control laws that feed back the entire state vector of a multivariable system, subject to some gains on those states, to try to control the system and create a new system in which we can change the behavior of the system however we want. So much like we did with PID control, we are essentially feeding back our some function of our state vector to create a new system with a new set of poles that will behave how we want it to. Okay, so let's just consider an LTI system. So at this point, you know the drill. We have a system of the form x dot is equal to ax plus bu, and an observation equation y is equal to cx plus du. Okay, and what we're going to do with full state feedback control is we are simply going to define our input to be some linear function of our current state, right? So our input u, let's just say that it is equal to negative k times x. Okay, so we're feeding back some function of our current state as an input. And let's see what happens when we do that. So we're going to substitute in negative kx for u in both of these equations. We have x dot is equal to ax plus b times negative kx. And we have that y is equal to cx plus d times negative kx. Okay. And if we just rearrange this, we get that x dot is equal to quantity a minus bk times x. And y is equal to c minus dk all times x. And you can treat this quantity here, let's just call this a tilde. And let's just associate this a tilde as being the new state matrix of our closed loop system. And similarly, we can call this quantity here c minus dk. Let's call this c tilde. And this is the new observation matrix of our closed loop system. Okay, so essentially we've created a new system. We've created a new state matrix, and we can select our gains k. So k is a matrix here of gains. We can select our gains k to place the eigenvalues or poles of the system wherever we want. So we can use feedback to essentially create a new system that behaves in whatever way we desire. Okay? And really that's it. That is full state feedback. Right. So throughout the rest of the class today, I'm going to be showing you some examples, and I'm going to be giving you some exercises of how you can complete this task. But this is essentially all full state feedback is. Okay, we are feeding back some linear function of the current state of the system and using that feedback to create a new system with the poles of the system placed wherever we want. Now, there are a couple caveats here. One is that from the name of this technique, you'll see that we need to have access to every single state of the system. Right? In practice, we might not have access to every single state. We may only be able to observe a subset. But as I'll show you in the lecture from Tuesday of next week, we can use what's called an observer to reconstruct the states that we don't have direct access to if that system is observable. Okay, so even if we don't have access to observations of every single state indirectly, we can use an observer to reconstruct those states for full state feedback. I'll also note that this control technique is essentially heuristic, right? So we're deciding essentially where to place the poles based on some kind of heuristic criteria. So we want it to be stable, maybe we want it to decay quickly. We may want it to track some reference. But it's not optimal, right? So on Thursday of next week, we'll be showing a way that you can select these gains optimally to achieve some objective function, and that will take the form of what's called linear quadratic regulation, or LQR. Okay, so there is a way to select these gains optimally. Today, we're just going to be showing how to do it heuristically to place the poles of the system in some pre-specified desired locations. Okay. Are there any questions on full state feedback? It's a pretty simple concept, right? It's going to be reminiscent of what we talked about with PID. It's just going to generalize and extend that concept. Okay, any questions on this conceptually before I move on? Okay, well, let's go ahead and take a look at a quick example here. So let's consider the LTI system. X dot is equal to -1, 1, 0, 2 times x plus our B matrix is going to be the 2 by 2 identity matrix, 1, 0, 0, 1 times U. So U here, our input is a vector, a 2 by 1 vector. So what we want to do first is let's verify whether this system is controllable or not. So first, is it controllable? So before we can do full state feedback, we have to determine whether the system is controllable. How can we do that easily? What's probably the easiest way to determine controllability for this system? So the easiest way to determine controllability for this system is probably the Kalman rank condition. So let's go ahead and construct the controllability matrix. It's given by B, AB. We know that B is just the identity matrix, so we can put that one in. And then AB, well, B is the identity matrix, so AB will just be A, right? So we can write -1, 1, 0, 2. Okay, what's the rank of this controllability matrix? Two, right? It has the identity matrix in it, so that gives us 2 rank for free. Essentially, we don't even have to look at the rest of these columns here. So yes, it is rank 2. So this system, is it controllable or is it not controllable? This is good to go. This is controllable, right? So because it's controllable, we can drive the system to any desired final state we want, meaning that we can also place the eigenvalues of the system wherever we want. We can essentially control the behavior of the system however we want to. Okay. So let's go ahead and define a feedback law of the form U is equal to -kx. Okay, we have that our B matrix is R2 by 2. Our U vector is R2. So what dimension does K need to be? So K also needs to be 2 by 2, right? It's the only dimensions that will allow this to work out. So we can define our K matrix as follows, just the diagonal matrix with K1, 0, 0, K2, where these K1 and K2 elements are the gains that we are going to be applying for our feedback control input. All right. Cool. So we know that our closed loop system will be of the form x dot is equal to A minus BK times X. Right. First of all, before I go further, is our original system stable or unstable? Can you tell what the eigenvalues of this system are just by looking at it? So I never explicitly stated this fact in class, but if you have a matrix that is upper triangular or lower triangular, then the eigenvalues are the elements along the diagonal. Right? And you can verify that just by taking the determinant. Yeah, so the eigenvalues will be -1 and 2. So is this system stable or unstable? Unstable. So let's see if we can figure out a set of gains that will stabilize this system. We have that our closed loop system is the form A minus BK. Okay, if we write this out, we will have -1, 1, 0, 2 minus our B matrix is the identity matrix, and our K matrix is K1, 0, 0, K2. All right, and this simplifies. If you carry this out, you will get -1 minus K1, 1, 0, and 2 minus K2. All right, so let's go ahead and see if we can find the gains that are going to stabilize the system. You can probably do it by inspection in this case. It's just not too difficult. But again, we can do this by taking the characteristic equation. So we have 0 is equal to the determinant of SI minus A tilde, where A tilde is our closed loop state matrix. We have the determinant of SI minus A tilde. That will give us S minus -1 minus K1, -1, 0, and S minus 2 minus K2. Sorry. Yeah, no, that's right. Okay, determinant. And if we carry out this determinant, what we'll get is S minus -1 minus K1 times S minus 2 minus K2 is equal to 0. So what gains do we need to make this system stable? What condition on the gains is needed to make this system stable? So which gain do we need to have a condition on here? K2, right? So we want to make this pole negative. So K2, we need to set to be greater than 2 for stability. Okay, and that is essentially feedback control in a nutshell, right? In this case, we had independent access to both of those states, so we could apply inputs to both of those states, but it may not always be that easy. So let's go through an example where it's not quite as easy to control the system. So we'll have the same state matrix. We have x dot is equal to -1, 1, 0, 2 times x. And in this case, our B matrix will just have this column vector 0, 1 times u. So now we can only control directly the second state. So first, let's verify that this is controllable. We have QC is equal to B, AB, right? So help me fill out this matrix here. What will the first column be? 0, 1, exactly right. And the second column will be 1, 2, the second column of A. So if you have A times 0, 1, it'll just select the second column of A. So what is the rank of this matrix? 2. And thus this system is also controllable. All right, so we have that U is equal to -kx. In this case, our B matrix is 2 by 1. Our U is a scalar. So our K matrix actually needs to be of dimension 1 by 2. All right, so we have that our K matrix is going to be 1 by 2. We'll just write its elements as K1, K2. And if we apply our feedback law, we have that x dot is equal to A minus BK all times X. If we write this out, we get -1, 1, 0, 2 minus our B is just 0, 1, and our K is K1, K2 all times X. And we can expand this out. We will get -1, -K1, 1, and 2 minus K2 all times X. Okay, so in this case, we can't really tell just by inspection what the gains need to be to make the system stable. Let's go ahead and just try expanding out this characteristic equation here. So let's look at 0 is equal to the determinant of SI minus A tilde. We will get lambda plus 1. Actually, let's call it S instead of lambda. S plus 1, -1, K1 and S minus 2 minus K2. Okay, and if we take the determinant, what we should get is 0 is equal to S plus 1, S minus 2 plus K2 plus K1, right? So these two elements minus these two elements, their product. And if we expand this out, what we should get is S squared plus -1 plus K2 times S plus -2 plus K1 plus K2 is equal to 0. Okay, so this is our characteristic equation with our gains applied. Let's say we want poles at a specific location. Let's say we want poles at S is equal to -3 and -4. How can we determine the gains needed to place our poles at those locations? Does anyone have any ideas? Yeah, so what's the first step we might want to do? Yeah, so we could start with 0 is equal to S plus 3 times S plus 4, right? And this expands out into S squared plus 7S plus 12. Is that right? Yep. So all we need to do now is we have that -1 plus K2 is equal to 7. And -2 plus K1 plus K2 is equal to 12. Right? And from this, we can determine the gains. We can see from this first equation that K2 needs to equal 8. And if K2 is equal to 8, then from this equation, we have that K1 has to equal 6. Okay, so if you have a desired set of poles that you want to achieve, and you can express your closed loop system in the following form, then you can determine the gains that are needed to place the poles wherever you want. Okay. So that's essentially, that's it when it comes to full state feedback control. It's really that simple. Okay, so what I'm going to do now is for the rest of the class, I'm going to give you a couple examples to work on. I'm going to work with you on these. I'm going to give you one example that you can work on by hand. And then the next example I'm going to give you is a bit more complicated, and you will need a computer for that one. Okay, so for the first example, let's just go back to our structural system. So we have our structural system. This one you can do by hand. I'm going to give you a little bit of intuition for this. And part of the reason I'm doing these in class is because I can't give you homework on these just for a lack of time. And so I want you to get a little practice just working on these. So let's say we have our structural system, but in this case, we have some controller, some actuator on the top of it. And this actuator can apply some input force, which we'll just call UT here. All right, we have for this state space system, our state space equation is given by x dot, x double dot is equal to 0, 1, negative k over m, negative c over m times x dot plus our B matrix is 0, 1 over m. Let's just call this U. Okay, so we have a state space equation. We have that x dot is equal to ax plus bu. And I want you to let our input u be given by the feedback law negative k times x. Actually, this u is a scalar, so let me just leave it like that. So we have that our input is given by this feedback law. Where's the, oh, I have it, okay. X dot then will be given by the closed loop system a minus bk times x. And our k, our vector of gains, is going to be the 1x2 matrix. Let's just call it k1, k2. Okay, so what I want you to do is, I want you to first write out this matrix A tilde. And then after you do that, I want you to write out the characteristic equation of this system for that A tilde. So I want you to write out the characteristic equation of the closed loop system. After you do that, I will give you a final instruction to work on. So just do those two things first. So first, write out A tilde. And second, write out the characteristic equation of the closed loop system given by A tilde. Okay, so I'll give you about 5 or so minutes to work on that. You can work with a partner if you'd like. And then after that, I will give you an additional pole placement problem to look at. All right, so let's go ahead and, in the interest of time, just give the answers for each of these. I think I saw most of you have gotten these already. So if we're looking at A tilde, that's going to be equal to A minus BK, which is going to be equal to 0, 1, negative K over M, negative C over M, minus this outer product of 0, 1 over M, K1, K2. Right. If you expand this out, you should get the answer 0. In the bottom left corner, you'll have negative 1 times quantity negative K minus K1. In the upper right, you'll have 1, and in the bottom right, you'll have 1 over M times negative C minus K2. Okay, so this is our equation for our closed loop system. And we can find the characteristic equation just by taking 0 is equal to determinant of SI minus A. Just in the interest of time, I'm just going to write out the characteristic equation for you. What you should get is something that looks like S squared plus 1 over M times, this should be C plus K2 times S plus 1 over M times quantity K plus K1 is equal to 0. Okay. Who was able to get this far? Who have got this answer? So I got a couple of you here. Does this characteristic equation look familiar to you at all? Does this look like something else that we've done? Yep, this is PD control. So if we called this K, if we called this KD, we called this KP, this is PD control. So it just so happens that for this system, where our states are the displacement and the velocity, this is equivalent to PD control. So the two concepts are the same for this single variable system in which we have access to the displacement and the velocity. With full state feedback, though, it doesn't necessarily need to correspond to PID control, although in this case it will. Okay, so yes, you got an answer that is equivalent to PD control. All right, so for our next part of this problem, this should take about 5 or so minutes, and then I'm going to switch to a more difficult problem for which you'll need your computer. Let's let M equals 1, K equals 2, C equals 3. So our state space system will be the form x dot, x double dot is equal to 0, 1, -2, -3 times x dot plus 0, 1 times u. What I want you to do is find k. So in other words, k1 and k2, such that our poles are at -6 and -5. Okay, and I'll give you about 5 or so minutes to work on that. And then we're going to switch to our more challenging problem. All right, so it sounds like quite a few of you have finished the problem. So who wants to volunteer the answer for the required gains to set the poles at -6 and -5? Anyone want to volunteer their answer? That is correct. So we can solve it using essentially the same method that we showed for the last problem, right? We write out what the system needs to be for those desired poles. We write out the characteristic equation, and then we know that our characteristic equation for our controlled system has to be of the form s squared plus 3 plus k2s plus 2 plus k1. And we just simply find the gains such that 3 plus k2 is equal to 11 and 2 plus k1 is equal to 30. And that turns out to give you k1 is equal to 28, k2 is equal to 8. Okay, so that is not so bad, right? And that's essentially feedback control. There you have it. All right, so in the last 15 minutes of class, you're going to finally get a chance to use your computers, which I promised you would get a chance to use. So we're going to go to our multi-story structural system. From homework 5, we had a 3-story structural system. So with positions, each of the floors has a displacement and a velocity associated with it. Each floor has a mass and a stiffness and a damping. And we showed that we could write this system in the following block matrix form. So we have that our system is equal to the form x dot is equal to 0, I, negative m inverse times k, and negative m inverse times c, where m is your matrix of masses, k is your matrix of stiffnesses, and c is your matrix of damping coefficients. And note that our state vector here is of the form x1, x2, x3, x1 dot, x2 dot, x3 dot. So what I want you to do is I want you to take this system. I want you to, so I will give you a little bit of code to simulate this system like we did in class yesterday. So I want you to code up this system. I want you to simulate it, simulate its homogeneous response to the following initial condition. So this would correspond to a velocity, an initial velocity of 1 at the top floor over the interval 0 to 20 seconds. So I want you to create the system, simulate the response. I want you to find the poles of the open loop system, so the system without control. Then I want you to, using feedback control, place the poles of the system at -6, -5, -4, -3, -2, -1, and find the gains required to do that. I'll give you a function call that you can use to do this in Python or MATLAB, so don't worry about doing it by hand. And then finally, I want you to simulate the response of the controlled system. Okay, so I'm going to give you a code example. So I've uploaded this a piece of starter code under files, code files, structure starter. And that basically just consists of these lines here, which you can also just copy yourself if you wish. So this gives you the structure and state space form. So I want you to use this to code up the structural system. And then I want you to do those 4 tasks that I showed you earlier. And as I said, there's a function call that you can use to place the poles of the system or determine the gains to place the poles. I don't have room to show it up here right now, but I will write it down for you shortly. It comes from the scipy.signal library, and it's called scipy.signal.placePoles. And in MATLAB, there's also an equivalent function called place. that will determine the pole placement gains. Okay, so I will leave this code up for a little bit if you want to copy this, and then I'm going to go back. Actually, would you prefer me to go to the instructions or leave this up? Instructions, okay, so I'll go to the instructions. Remember that this code is uploaded here under files code as structure starter.py. And you can just copy that into a notebook if you wish. Okay, so I'll write in a couple hints here. Oh, yes, and work with partners, please. So groups of 2 or 3.
And then so